Time out just for a second. If you need one of the little Ohm's Law wheels here, I've got a bunch of these from way back in the DC circuits time, but we will use Ohm's Law a little bit today. If you need one, I got them here. If you need a reminder or refresher.
I sent out a Hands Club online reminder, it had my call sign on it.
I saw that, but I figured, what difference does it make? We got the word out, that was the main thing.
I don't proofread. Terrible at it. Oh, there's that.
You know, on second thought, you and I were talking a little earlier, maybe it might have been a bad choice to make this a holiday weekend.
Oh, I didn't even realize it. I don't do a lot with holidays,
Yeah,
so, yeah, I didn't even realize it.
yeah.
Because it's August, I didn't even look into September.
Yeah.
Yeah, we may have to redo this one at some point.
And it is going to be Labor. Anybody going to labor on Labor Day?
Yeah, usually.
Well, Chris does. You gotta work.
You got to work? Okay.
Those people with cancer don't stop being sick. just 'cause
I
it's
understand that. They don't take a holiday. Yeah. We're going to have our little camper over at Bonham State Park. We're having two of our great grandkids visit with us, one at a time, because our trailer only sleeps one extra besides my wife and me. So that's our excuse for just taking one at a time. So we'll have 5-year-old great grandson Tuesday night, and then the 7-year-old great granddaughter for Wednesday night. And I'm concerned about him. I'm not worried about her. She's been with us before. She can take care of herself. She can entertain herself. She can read. She's very independent. But he is very, very needy. He just wants to cling to you. He's got to be talking all the time, and he just wear you out. You know, why is there air? Oh my goodness. Do worms yawn? You know, heavy-duty theological questions.
Wow, smart kid.
Yeah, but anyway, it'll be interesting to see. The part of the deal was to let them swim in the little lake there. You know, and they got a nice little swimming area there. But it may be a little chilly for that. I don't know.
In Ohio, we swam when it was 70.
Just didn't worry about it.
Water was still warm. Well, no,
Yeah.
it wasn't, but
If we don't have a whole lot
It
of
was
rain,
warm enough as kids.
yeah, kids, you don't care. If you don't have a whole lot of rain, water will probably still be okay. If we get a lot of rain, though, that'll probably cool the water a little
when
bit.
we drove up to Alaska, we boondocked at a park, and there was an event going on, and these kids came out to the dock with their swimsuits on, and they were sitting there in a rubber tube, just sitting there on the deck talking, and then finally they started going down the slide and swimming, and the water was about 40 degrees. I told Andrew, I guess we're gonna have to do a water rescue. But they were fine.
Yeah, kids are very resolute when it comes to that sort of thing. Yeah, they are.
And I knew a kid that talked like that too, Bob. And I asked him one time, Eric, why do you ask so many questions? And he looked at me like I was stupid and said, because I can talk. I got some better answer.
Got to keep it exercised. Oh my goodness, yes. Okay, all right. And with that, let's jump in the water here, as it were. And let's see, left and right. Okay, solid state devices. Things we're going to try to do today with a little bit of luck. We'll use some of the different instruments. Tim brought his scope. I've got a scope up here, and I've got a couple other portable scopes over here. I didn't bring the big honkers because they're just too much trouble to carry around. We'll use the scopes a little bit. A couple of you already been using the multimeters, checking batteries, which is always a good thing. Those batteries stay in these little boxes, and they don't always get exercise. They may or may not be good, so it's a good idea to check batteries. The handouts, there's several handouts, including the ones for the things that we do that lead you step by step in what you hook up, what to do with the wires and so forth. We'll start with diodes and talk about diodes, because they're the basic building blocks for the solid state world. And then some transistors, which came right after the diodes. We'll talk about them just a little bit. And then mention some of the other things like silicone control rectifiers and triacs and diacs and stuff like that. And a little bit about integrated circuits. Integrated circuits are just a way of doing a lot of diodes and transistors in a small package. And then decide, do we want to do a digital class next, or do we want to do the vacuum tube class? And we'll talk about the differences between those a little bit later on toward the end. Sir?
Camera can't see you.
Sorry, I forget. I forget that I'm on candid camera here. All right, with that. Some differences between transistorized gadgetry and tubes. This is an old picture, as you can probably tell. The transistors that is showing up here are relatively big compared to what most of the ones we'll see now. If you look in your package, you'll notice you have this tiny little black speck with 3 wires sticking out of it, which is a transistor. And that even is fairly large. When we get into the surface mount devices, which don't have the long leads like that, they can be almost just a speck. They can be so tiny. So they make them a lot smaller. Those are all vacuum tubes in the right. The little ones were some of the efforts that we had in making tubes smaller. I remember back in the dark ages working with a guy who sold hearing aids early on, and they were vacuum tube based hearing aids, believe it or not. And they used those tiny little metal can tubes in there. The hearing aid was about the size of 2 boxes of what we used to call penny matches, the little boxes of matches, about the thickness of that, about that size. So it's fairly big. Used a 22-volt battery, which would last about 12 hours, but it would run the thing, and it was actually a pretty decent hearing aid. But fortunately, we've come a long way, and we're not using the tubes that much. Tubes are still around, by the way. Where do we see tubes, in the amateur world anyway, where do we usually see tubes most today? Amplifiers, big RF amplifiers. A lot of those still use, what's it, 807? What's the tube we use for a lot of the amplifiers? I think it's an 807. I think it's an 807. Anyway, it's a big vacuum tube because it'll handle the power primarily. Okay. Why do we study these things? Because they're the building block of most anything we do today. Even if it's an integrated circuit, it's still what makes it work. My wife asked me an interesting question when we were packaging some of this stuff up. She said, well, why do I need to know all this stuff anyway? Can't I just operate the radio? Do I have to know how it works to operate it? Well, no, you don't have to. But I think it makes more sense if you do know a little bit about what's going on under the hood, and especially when something doesn't work right out of the box like it's supposed to. You have a better idea on where to go to fix it, to make it work. So that's kind of why we get into this sort of thing, give you a better understanding of what's going on under the hood in our radios. Anyway, the solid-state devices, as I said, are pretty much the core of everything we do. The handling precautions are not nearly as pronounced. Come on in. They're not nearly as pronounced today as they used to be. Solid-state devices used to be really, really static sensitive. Not so much anymore. However, if you're doing very much of this, especially if you're working for somebody else, we use a thing called a static strap, which is this blue thing down on the lower right. Basically, it clips onto a ground source, some kind of a ground anyway. It goes around your wrist, and that keeps static buildup from staying in your body. So when you touch something, you don't get that zap. It's kind of like when on a cold morning, you shuffle across the carpet and touch the doorknob, and it goes zap. You do that to a transistor, and you have literally just zapped the transistor. It'll take it out. So that prevents that from happening. A lot of people use a static mat, which does basically the same thing. It's just kind of a rubberized mat you put on your bench. Has a ground lead on it, grounds to some ground, good ground someplace. Takes care of the same thing in a local grounding operation. Okay, diodes, transistors, Zener diodes, LEDs, SCRs, triacs, integrated circuits. For the integrated circuits today, we're going to be looking at optocouplers, sometimes called opto-isolators. But basically, it's an LED and a transistor all in one little integrated circuit, which makes it kind of an interesting piece to look at. Kind of gives us the best of both worlds. Okay, some advantages to solid state. We get, out of most of the solid state devices today, we do get good gain. Now, what is gain? Anybody? Increase in signal level. We have a small signal in and a large signal coming out, called gain. With most transistors, we can control the gain if we need or want to by how we bias or the kind of voltages we apply to the transistor, and we can predict that. There are formulas we can use to predict what it's going to do. They're very reliable because they don't generate so much heat as vacuum tubes do. They tend to be very, very reliable. That was one of the big deals with vacuum tubes. They generate so much heat. The computer that I went to school on for the Air Force back in, Good grief. 1969 was an IBM Q7, as it was called. It had 53,000 vacuum tubes. It was literally a vacuum tube computer. And it just had banks and banks and banks of vacuum tubes in a room. And this thing it had 4 1-megawatt generators to power it, of which 3 had to be online all the time. You could take 1 down for maintenance, but 3 had to remain online. If you lost power and the air conditioning stopped, the cooling ventilation stopped, and you were in one of those rooms with vacuum tubes, they cautioned us that you have about 30 seconds to get out. Beyond that, the heat will rise so quickly that it will overcome you and you won't be able to get out. So that gives you an idea how critical the heat issue is with vacuum tubes. We talked about a vacuum tube amplifier, RF amplifier. They're great, but they do generate some heat. They've got to be ventilated, well ventilated. Transistors, not so much so. Now, yeah, transistors can get hot. Don't take that the wrong way. They can get hot and need to be cooled or ventilated, but they don't generate nearly so much heat as vacuum tubes. They don't have a filament to start with, a little glowing wire inside there. They're generally fairly simple. Take a little transistor, takes 3 leads to make it work. Take a vacuum tube, you got a plate and a plate and a cathode and a heater and a grid that comes in, so you got a lot more wires and pieces to deal with than you would with a transistor. Size, as we saw in that first slide, generally the transistors can be very, very small. Diodes are very, very small. Now they can be big, and that's not to say they can't be. If we get into power handling devices, they can get very large. And then power consumption in and of itself is generally much less. How many of you remember your first transistor radio? Little AM pocket radio, remember those? Yeah. Put one on your wrist even. Would run over on a 9-volt transistor battery or a couple of AA batteries, which we couldn't do with the vacuum tubes. At one time, I actually had a vacuum tube portable radio. It was about so big and so deep and weighed about 5 pounds. Took 3 batteries in the back, to make it work, and it would run for a couple hours before they used up the batteries. But it was portable, But then the transistor radios came along and we loved it. So power consumption is dramatically less. Some disadvantages at the same time. Now the reliability generally is not an issue these days. Early on, reliability could be a problem. Transistors had to be very carefully selected, and you had to be very cautious, especially in critical applications, to make sure they were going to stand up. Today, that's not generally the case. They're very, very solid. They can handle power. If you use a large transistor, a heat sink under it if you need it, but they can dissipate a lot of power if they need it. They do have some heat buildup. Generally, they're mounted on a heat sink. You have a fan on there. Most of our power supplies are solid-state power supplies, but you notice they always have a fan, and that's to help keep them cool. Frequency response can be an issue. Because of the internal construction of a transistor and the way the pieces are in close proximity, you can get some stray capacitance that causes a restriction on the higher frequencies. Now, we've come up with ways today to eliminate a lot of that and other types of transistors besides what we initially started out with. So we've overcome a lot of that too. The size can be an issue either way. They can be so tiny they're hard to handle, as a matter of fact. We'll see that here in a little bit when you take those transistors out to test them. If you got big fingers, it's hard to get those little leads all separated out and see what you're doing with them. Likewise, if you're doing a big power transistor, size can be an issue if you have limited space. A little bit of drift, that was one of the issues with early transistors in particular. As they warmed up, they would drift back and forth. The gain would vary on them, and the amount of leakage they would have would vary as the thing heated up. A lot of that has been resolved today. It's not so much a problem. And in static sensitivity, vacuum tubes really don't care. What do you know about the big magnetic pulse we hear about? That if the big atomic bomb comes, they release this huge magnetic pulse. It's going to wipe out all of our radios. What's that about?
About the induced voltage in any conductor and how it will destroy the PN junctions in
Exactly.
semiconductors.
And that's exactly right. We have this huge magnetic field which will generate currents in the wiring and in circuit boards and everything else. And the fear is that it will be so much, it'll be like a huge static discharge. It'll wipe out the transistors, which are inside the integrated circuits in most cases. That may or may not be true. We'll see. A lot of the transistorized stuff now has built-in circuit protection, but will there be enough voltage generated by that magnetic spike to overcome the voltage protection and burn it up anyway? We don't know. Why do we say, but if you've got a vacuum tube system, it's not going to affect it? What's the difference?
Because it doesn't have the same type of p-n junction.
Exactly. The vacuum tubes are accustomed to dealing with high voltages. They run on high voltages, where the transistor runs 1.5 volts to 2 or 3 volts oftentimes. Most vacuum tubes need 100 plus volts for the plate voltage. So they're accustomed to dealing with high voltages. So generally speaking, if you have a vacuum tube here, it would survive that. Let's hope we never have to find out. Okay, diodes is kind of the starting place. What does a diode do? Let's talk about that first. What's the purpose of a diode? What's its function in life? Anybody know off the top of your head? By the way, you have a handout sheet that lists all this. If you want to take notes on it, feel free to do that. It follows right along with what we're talking about. So if you want to write in there, go ahead. Larry? One-way route. Idea behind a diode is it lets current flow in only one direction, which works out good. Why would that be important? Because we can do a lot of things with that.
I think you said one-way valve.
A one-way valve, same thing.
Which also is the old name for the tube.
Yes. Well, if you talk to anybody from Great Britain, they still call them tubes valves. You'll see in their literature, like if you get the Amateur Society of Great Britain, they'll talk about the valves. They'll talk about tubes, yeah. But it allows the current to flow in one direction through the device. And we can use that for a lot of different things, from power supplies, detectors, rectifier, you name it. We'll talk about a lot of those things that we can use. Early on, germanium was used in most of the diodes. Germanium is a little bit leaky. And that is to say it didn't have good isolation front to back. It would have a little bit of leakage backward through the diode. Also didn't handle a lot of voltage. We came along with a way to use silicone in that. Silicone overcome a lot of that, cut down on the leakage, would let us use a lot higher voltages and currents and everything else. We use the word rectification, which refers to the current only flowing in one direction. When we look at the AC current coming out of the wall, the reason we call it AC, it's alternating current, meaning that the current is not flowing in a straight line all the time. It rises to a peak, falls back to zero, goes to a negative peak, goes back to zero, and does that at 60 times per second for household current in America anyway. So we can rectify that by using a diode. Rectify meaning we can solve the problem in this case, because that diode will only allow current to flow in one direction. We can use it to convert that AC to DC, which most of our equipment needs in order to operate, needs DC power to operate. So it will let us do that, rectify that thing by allowing a current to flow on in one direction. It can also be used as a detector. Anybody ever build a crystal radio? If you did, well, even if you didn't, it doesn't matter, it works the same way. The crystal radios used usually a germanium or some similar kind of a crystal. And basically what it did was it would rectify or take care of part of that AC signal that was coming in and leave you with just the audio portion, which is what you're wanting to hear. And the rectifier, the diode, did that for us. And then a switch, it can be used for switching, and we see this in a lot of computer systems. Different series of diodes with different voltages applied here and there can allow something to turn on or turn off. Steering diodes, as they're often called. Then we put diodes together, we make a transistor. With a transistor, we can do a lot of things. Again, germanium and silicone, the early transistors were germanium. Anybody remember a CK722? That was one of the earliest transistors. If you were way back when, if you were trying to build your own little transistor amplifier for your crystal diode radio, you used a CK722 made by Raytheon. But it was a germanium transistor. You had to be really careful with it that you didn't overpower it and you didn't static shock it and blow it up. Then we went into silicone, which makes it a whole lot easier for us to work. And then they do all kinds of chemical mixes as well, which helps. Transistors can be used as a switch, turn something on, turn something off. Used to amplify, as we said earlier, a small signal in, a larger signal coming out. And then it can do it as a control function to control things turning on and off, switching on and off, and so forth. Okay, back to diodes. This is just a way of depicting a diode. One side of the diode is called the anode, the other is called the cathode, as you can see there. Let me see if I can get, does this work okay like this? Okay, the little bar sign is always the cathode. The little stripe on it, if it has a stripe in it, normally will indicate that that's the cathode. If you look in the little package of parts that you should have 3 diodes in there. There should be one that's a little, Larry, you need some goodies, don't you? Here you go. We got you covered. Keep your seat, you're fine. Okay, well, if you look in that little package, you should find 3 diodes. There should be one that's kind of a clear glass bead looking diode, a real tiny thing. And then another one that's looks maybe a little more sturdy, that's kind of a glass, more or less transparent. And then there's this one that's solid black. Each one has its own function. Can you find it?
More that have a different function.
Pardon, please?
There are 3 more that have a different function. Red, green, and yellow.
Well, if you get into that.
Like emitting diodes.
Yeah. We're keeping it simple, though. We're keeping it simple. Okay, if you look at that, those 3 diodes, one of the things you should find that they have in common, they all have a stripe on them. You don't have diodes in there? They can be a little bit elusive because they are pretty tiny. Okay, that's what they look like. Can you see that from where you're sitting? Probably not. They're tiny. They're tiny, which is the great part about it, you know? Okay. You just dump them out on the paper if you want to. That's what you're looking for. Okay. Okay, that's yeah. You found your 3. Okay. That's what they look like. Okay. They're tiny little things. Jerry just mentioned magnifying glass. I fully intended to bring one and totally forgot it. So if you have a magnifying glass, don't feel bad about using it. Most of these are marked with numbers, tell you what they are. But again, you may need a magnifying glass in order to see it. Okay, the black diode, let's talk about it first. Should be a 1N4000 or 4001 series. I think it's 4001. The 1N4000 series diodes were a real good standby diode for everything in the world, often used in power supplies and various things. They come in 1N4001 through 4007, each higher number handling a different voltage. Now, how do we rate diodes? Maybe we should talk about that first. How do we rate a diode as far as what it can handle? First is the voltage. How much voltage can it handle? When the voltage is going through in a positive direction, the diode turns through. By the way, the voltage is always going to flow into the arrow, going that way. I use the conventional positive to negative current flow, not Navy flow. But anyway, so it's always going to flow that direction. So when current is flowing in that direction, the diode's turned on, flows right on through. When the voltage reverses, though, and it can't do it, and this blocks it from conducting, then the breakdown voltage is that voltage which, if you exceed that, it will blow up the diode. So that's what the voltage rating is. If this is a 50-volt diode, then this says it can handle up to 50 volts, but if you put a reverse voltage of 55 volts, you may blow it up. That's the idea. Second thing that they're rated in is amperage. How much current is it capable of handling? These are supposed to be 1 amp diodes. I think it's 1N4001, I believe, is 100 volts. Does that sound right, Tim? I think a 1N4000 is 50 volts, 1N4001 is 100 volts, I believe. Anyway, they're just a standard low diode. They're cheaper than dirt nowadays, but we use them for a lot of things. And we'll use this one in a minute when we build a power supply. Okay, the other 2 diodes that you have work the same way, but they have different purposes. And unfortunately, you really have to have a magnifying glass to pull out any of those numbers on that. I can't see it at all. But you notice they're little glass beads. So inside that little glass bead, is a small speck of silicone material, or in the case of the 1N34, it's actually a germanium material, and a little touch point on the thing that touches it and makes contact with it. These are called small signal diodes. The 1N34A was the one that we used in our crystal radios way back when. It was germanium, because the forward voltage drop on the germanium is much less than the silicon diode. So it would allow us to deal with weak AM radio signals. Again, without a magnifying glass, you really can't tell which is which. These are just for us to look at more than anything else. The other one is a 1N4148, which is a real standard diode used in switching applications, computer applications, things like that, logic applications, and so forth. So it's a silicon diode, handles a greater voltage, and it's a very fast diode. We also can rate the diodes and how fast they can switch back and forth. And if we exceed the frequency at which they can that they can handle, then we can also obviously blow up the diode if that should happen to us. Okay, so big thing to remember, current always flows into the point from cathode to anode. When the current goes the opposite direction, it gets blocked. We'll see that happen here in just a minute or two. Okay, another type that we want to just mention real quickly is a Zener diode. Notice this little funny, almost looks like a Z across the bar symbol. A Zener diode is a special kind of diode that's used for voltage regulation. So generally what we do is we would connect this diode along with a resistor across a power supply and read the voltage then from ground to the top of that Zener diode. And the great part about it is that Zener diode will always maintain that voltage within reason at least. So it's a real cheap way of doing a quick power supply or quick voltage that you need where you know what voltage you want. Again, they're rated just like the others. They're rated for the amount of voltage they can handle and for how much current they can handle. You can get, a 500 milliamp diode, you can get a 1 amp, you get a 3 amp, 10 amp, etc. And then they're rated in voltage. You can get a 3 volt, 5 volt, 6 volt, 9 volt, and then almost anything in between that you want. And we'll show that again a little bit later on. But pretty much still marked the same way. A little cathode marking there lets you know it's there, and an additional mark lets you know it's a Zener, generally speaking. Okay. Thoughts, questions, heartburn, headaches, etc. Clear as muddy water on a clear day? Okay, good. Moving right along. P-N junction. This is what makes it work. We have a piece of P or positive material, a piece of negative or N material made of silicone type, glued together in the middle, we call the P-N junction. And that P-N junction is what makes it actually work. It's what tells the diode whether to allow current to flow or not. So again, current here going from positive to negative, going zip through there, bap, bap, and back through a dropping resistor. That's not particularly significant, just another way to look at it. Okay, this illustrates the actual using of a diode for current flow. In the first case, current's going to flow from negative through the light bulb, hit the diode and say, uh-oh, I can't go through there. Hence, the light doesn't come on. But if we go the other route, we flip the diode. Notice the difference. This diode is this way, that one is the opposite direction. So now we go minus through the light bulb, the diode turns on, allows current to flow, and the light bulb turns on. Very simple. And we use them for all kinds of things related to that. Pardon?
Why would you put it in so the light doesn't go on? Watch me work.
I'm sorry.
Here's another idea, just an example of how that would be used. You would put the diode in forward on the power connection to your radio, for example. Your radio probably has one put in this way. It is designed to handle all of the power and current that your radio can handle. So let's call it 15 amps. If you hook the power leads of your radio up to a battery correctly, the diode is invisible. It lets the current flow the way it's supposed to. If you hook the power leads up backwards, the diode prevents the electricity from going through your radio.
Exactly.
And thus blowing it up.
That's
In that
exactly
case,
correct.
it's used as is what we call it.
Interesting tidbit about that. Yeah, I have personal experience with that firsthand. with an ICOM radio, a very nice little ICOM D-Star radio that I had out at Field Day about 3 or 4 years ago, and was doing the go-to station, and I wanted to hook up this ICOM radio and see if I could catch a D-Star repeater, and without thinking, hooked it up to my battery, and like, what's happening? All of a sudden, this smoke started to come out of the radio. You know, that's what makes all things quit working. You let the smoke out. You know, you let this magic smoke out, and they don't work anymore. And to make a long story short, the radio had a protective diode in there for that purpose, but the protective diode depends on the fact that you also have a fuse in the line. So when you hook it up backward, it'll see that and it'll blow the fuse instantly.
That's a different, yes, in that case.
And I didn't have a fuse in that line to the battery.
And in that case, they did the protective diode. There's two ways to do the protective
Yeah.
diode. One, the one I described as in series, where it stops the current from going to the radio. The other is you put
Across.
the diode in backwards so that it's between the two leads. When
Yep.
the radio's hooked up correctly, the diode does nothing. When you reverse it, the diode
Gives you,
passes all of the
gives you a
current.
short circuit across the input
And
leads.
so
Yeah.
in theory, no current goes into the radio itself. The diode absorbs all of the energy and is supposed to blow your fuse.
Right, if you have a
But if
fuse.
your fuses aren't in the line, the diode will then blow up. And when the diode is now gone, the radio will then.
And then all the smoke comes out of all the components in the radio. And that's exactly what happened. By the way,
There's ways to do a protection circuit, and I don't particularly care for that method.
by the way, that same battery now has a fuse on both sides. It has fuses on both sides now, so I want,
Use is the preference.
in case I ever do that again. So diodes are very, very important. Now, how do we test these guys? This is where you're going to need a meter. So how do we test it? All the meters have a diode setting. If they don't have, then you just go to the ohm scale. And basically, we take our ohm meter, and I'm going to back up one slide. Maybe. Okay. We take our little ohm meter, and we're going to hook the leads across this way and measure. Then we're going to flip the leads the other way and measure. One way we should read a very high resistance. The other way we should read a very low resistance, which tells you the diode is good. If you don't get the low resistance one way, that tells you the diode is open. If you get more or less zero resistance both ways, that tells you the diode is shorted. Okay, and that'll work on all these different diodes. Now, the readings will be a little different, depending on whether it's silicone or whether it's germanium in the makeup, but it works the same way.
What should we be on?
If it has an ohm scale, if it has a diode scale, go to diode. If it doesn't have, then go to a low ohm scale. You need a meter? Let me get you a meter. By doing the resistance checks on the thing, can you figure out which one is the germanium diode and which one is the silicon diode?
Of the two glass ones.
The two glass ones are, one's silicon, one's germanium.
Right.
But which one's the germanium, which one's the silicon?
So you remember
You tell by the resistance.
why does one?
The germanium will have a lower resistance reading than the silicon. The silicon will usually run somewhere around 600 ohms. The germanium will usually run somewhere around 250, 300 ohms. It's a lower. Okay, now, that being the case, also you might notice, if you pay attention, when you hook the leads to the diode, when you put the negative lead to the cathode, that's when you get a good reading of 600 or 300 ohms. When you reverse it and you put the red lead on the cathode, that's the bar end, then you get an open circuit. Or the little bar on the diode. Yeah. Okay, and I didn't realize initially that the little red or yellow multimeters do have a diode scale on them, which works out nice. Because you have to have enough power provided by the meter to turn the diode on when it's going in the forward direction, where the ohm scale may not have enough juice to do that. Are we good with that? Okay. Now then, let's talk about the Zener just for a second. So in this case, we're just using a 9, for illustration, we're just using a 9-volt battery to give power to this thing. Negative side on there, positive coming out the top. So we're coming out, we're coming through this zener. So wait a minute, that's backward. For zener, actually it's not. And then we're going back to the plus through the resistor. But the idea behind the zener is that the zener, this particular one I chose for the illustration there, used a 5.1 volt zener, rated at 1 watt, which would be about an amp or so. So basically, if I come out here and I put my meter here and read the output voltage, I should read about 5.1 volts, or around 5 volts. And then the resistor has a very, very, very important function. Essentially what's happening with that resistor is it's playing the balancing agent. If I pull a lot more current, which would tend to make the voltage on the zener go down, then the resistor will allow more current to flow through. At the same token, though, I have to have the resistor. If I didn't have the resistor, then I would blow the zener diode because there's nothing to limit the current going through it. Does that make sense? Now, just for granted, let's go back to Ohm's law. Using a 33 ohm resistor and a 9-volt battery, what is the maximum current that can flow through that circuit? Do you remember Ohm's law? Lance, can the camera catch this over here if I draw on the board? An Ohm's law current is equal to voltage divided by resistance. The voltage is 9 volts, right? And the resistance is 33 ohms. Somebody with a calculator real quick, what's 9 divided by 33?
0.272737.
Is it 0.27? My black marker is not very good. So 0.27 amps, or 270 milliamps, if I want to put it in milliamps. So 270 milliamps, I'm probably okay, if the maximum current were flowing through this thing. Now, how do I figure out the wattage that's involved? Power is equal to IE, PIE. Let me see if I got something that writes better than that one. Okay, so the current is 0.27 times 9. What does that come out to be, somebody? 30? 3.3. So I could actually have 3.3 watts possible there, couldn't I?
Well, that would be the total output of the battery.
Yeah, the total output of the battery going through just the resistor.
The amount of
So
power going through the zener diode, since the zener is going to regulate it at 5.1 volts.
Exactly.
27 times 5.1.
right,
You'd be right at your 1 watt.
right. So anyway, that's the idea behind the zener diode. Now, we're not going to do a zener diode in here. I didn't bring any zeners with me, but that's what it's for.
No, the zener plus the diode equals the whole circuit. The zener is only a zener diode conducts any amount of voltage higher than its rated. The zener is rated at 5.1. In an open circuit with that 33 ohm resistor, you're still going to measure just shy of 9 volts on the other side with no current flow. Because there's no current flow, you have no voltage drop across the resistor. As you start to draw current, you start to have voltage drop across that resistor until you get to the zener diode. The zener is going to conduct everything higher than 5.1 volts. So if you've got 9, it's going to be dropping 3.9 volts.
Exactly.
That current flow, by the time you get done dropping across that resistor, you'll get 0.27 amps. And the zener is going to be taking all the rest of that voltage and giving you your 5 volt rated output.
If it makes it easier to visualize it, sometimes it's easier to redraw it like this, so that the resistor and the zener are kind of one on top of the other. We're taking the output right across the zener itself. That makes it more obvious of what we're doing. So basically the resistor is acting as a buffer to allow this to remain at a steady 5.1 volts. When I'm pulling current from this, then if I pull more current, then the resistor will drop less, and this will drop more of it to keep that at a constant 5.1 volts. So it's kind of a balancing act sort of thing that we're doing with that. Okay. But anyway, as I said, we're not going to build up a Zener. We are going to build a little half-wave rectifier power supply here in a little bit, but that's the deal with the Zener. Just want to talk about it so you know what it is. If you see it, you'll know what it is. Okay, talk about power supplies a little bit. This is probably the simplest form of a power supply that you can have. We have a little AC transformer of some kind over here. Gives us a nice sound wave out, AC sine wave. But our equipment needs to have DC, so how do we do that? Well, that's the function of the diode here. The R is just a load, something to load it just a little bit, make it so we can read it. And then the capacitor is there to smooth it. We'll talk more about that in a second. So how's this thing going to work? So basically, when the negative side goes around this way, it's going to go through, boom, through the diode and back down. But when it goes the opposite direction, the diode's going to block it. If we look at the sine wave, or look at the wave coming out here, this is pretty much what we see. Without the capacitor, now capacitor is used to smooth it or fill in the gaps. Without the capacitor, we would just see the tips of the sine wave like that. What happened to this other half of the sine wave that came in down there? We're not seeing this at all. What happened to it? It's being blocked by the diode, which is not good in a way. It's good because it's doing what it's supposed to do, but we're wasting half of the cycle. Half of it we're not even using. We're just ignoring half of it. Now, for a real low current supply, that works real fine. But if we're doing a higher current, and we need something with a lot of current, then we'll use a full wave rectifier instead of a half wave. But anyway, so what we see coming out of this thing without the capacitor would just be this little pulse thing like this. Then we put a capacitor in. You remember a capacitor's function in life is to charge and discharge. So when the voltage rises, the capacitor charges to its full capacity. And then when the current stops, that is, the alternation goes the other way, the other half of the cycle comes along, the capacitor starts to discharge into the circuit and fill in the gaps. Make sense? So what does that tell us about the size of the capacitor? Needs to match the drain that you're going to expect out of it. The more current drain you want out of that supply, the larger the capacitor is going to need to be. If there's very little current drain, a very small, 10 microfarad capacitor is fine. It'll take it just fine. But if you're going to pull some current out of it, then you're looking probably 100 or 1,000 or who knows how much. Whatever you need to do to make that happen. So that's the idea behind it. We're actually going to build one of those here in just a minute. We'll come back to it in just a second. So how do we not waste half of that sine wave? One of the ways is to use a bridge rectifier. We can get a bridge rectifier made into one little tiny capsule package, or we can make it with 4 individual diodes if we want to do that. But it's always depicted like this circuit shows it, so we'll go through this, how this thing works now. Okay, so we're coming along here, and our sine wave is giving us a negative voltage, so the negative goes through that diode, out, goes to our load, comes back in here, goes this way, and I'm sorry, I went the wrong way. Negative this way out, through the positive back here, and back over again. What happens when it flips the other way? Okay, then, let's see, that was with this one. If this goes negative, then we go here, zip, out, come back in again, through that one, and back out again. So we're always using 2 diodes that way. 2 diodes for one half of the cycle, 2 diodes for the other half of the cycle. That way we don't waste anything coming out. So if we looked at the sine wave out, or looked at the output from that one, where the other one just had this little thing like this, where this half is missing, now we're going to see this. So we're not missing that half of the cycle. So this end is much easier to filter to make it smooth DC than the half wave is. So if I'm using one of these little rectifiers and the capacitor goes bad, how might I know that it went bad in my radio? What might be an indication that I've lost a filter capacitor?
Well, it sounds like this.
Let's get okay. Actually, get a buzz.
A buzz.
Yeah, you get a buzz. We're thinking here, but using 110, 60 cycle kind of stuff. 60 cycle will give you a real buzz in the radio in the background all the time, which is a dead giveaway. Oh, filter capacitor's gone bad in the power supply. Tim, you start to say something?
Nope.
Oh, okay. Feel free.
So you might go to your other slide where you showed the capacitor and the output waveform. If you saw that it shows you in his, see how it looks kind of like a sawtooth?
Yep.
If you had in between each of the little lumps, the little dotted lines,
Yeah,
if you had another lump in the middle, which is what you get with full wave rectification,
right.
that sawtooth waveform looks more like smooth DC out.
Exactly.
Okay?
More
So
like this.
when you lose half of your rectifier, you get this sawtooth, and you will hear that in the
Yes.
speaker of your radio.
I
Yes.
think I know what you're talking about.
Your
I think
radio
I've heard this
is-
before.
I mean, you can
It's
hear it
obvious.
in the amplifier, just touch the middle pin. Your body acts like an antenna and picks up all the stray AC in your house. Like the hum of a microphone, exactly that. That is the exact sound.
Okay, so that's the idea behind that one. Now, in the digital class, we do try to do a full wave rectifier for that and give us 5 volts to do what we need to do in our digital. Okay, going on. Another picture with some waveforms there shows what we were just talking about. You see, as Tim was talking about, where the waveform is filled in now, it's much easier to filter than before.
Can we get a copy of your slides?
Of course.
That'd be cool.
Of course, you can have a copy of the presentation. I'll email it to you, or we can put it on the website, or we can do anything you want to do, I'm good for. Okay, yeah, I can email it to you. It's not, and this one doesn't have any videos or weird stuff, so an email's okay. It's fairly small. Okay, same thing we just talked about. Now then, let's build one. This is basically what we're going to build. So in your little package of stuff there, you have the little transformer block. That's this little guy here, just a little very low voltage AC transformer, 400 milliamps output, so 4/10 of an amp out. You can't get shocked with that. That's one of the reasons for choosing that. If you short it out, it's not going to burn anything up, but it'll give you enough to do what you want to do. So that's going to give us the transformer on the left, the AC input. Then we're going to use that 1N4000, that's the black diode. We use the black diode, put a load resistor and a capacitor, and then we'll plug it into AC when we get to it, and we'll put a scope across it, and we'll take a look at it. Now, in your package of handouts, you have a 1, 2, 3 step-by-step thing there that tells you what to hook up. So if you want to if you can follow just doing it rote, go ahead, but if you need to follow the instructions are there. It will tell you exactly what you need to do. That's called a simple half-wave power supply handout. That's this one right here. Shows the same little diagram at the top of the page. Tells you exactly what you need to do.
Right?
Okay, gang, let me get your attention here just a second, okay? Let's go ahead and look at the next section of this. We're going to talk about LEDs, light-emitting diodes. We're going to use this little power supply we just did and convert it into an LED tester so we can test LEDs. But we need to talk about LEDs first. Okay. You with me, gang? With me? Here we go. Sit tight, buckle the seatbelts. Here we go again. Let me pick. All right, this just has all the same instructions that you have printed out on what to hook where and to check it out. Look at it. Now then, let's talk about LEDs. Light emitting diodes. They're basically just a special form of diode that has some special doping or added chemicals added to it that when you forward bias or you let current flow through it, it lights up. That's it in a nutshell. Depending on what kind of impurities you put in it will determine what color the LED happens to actually be, whether it's going to be red or green or blue or yellow or white or whatever. Now, they're still just diodes. That's the ultimate thing to remember. 2 or 3 things about looking at diodes. When you see the symbol, you remember the diode symbol by itself did not have these 2 little arrows. It just looked like that. We put the 2 little shooting arrows from it, indicates it's an LED. It's emitting light. So when you see that symbol, you know that means LED. How do you identify the cathode and the anode? Generally speaking, the 2 leads are different lengths. But what if you get one, somebody's clipped them off where they're the same length? You can try to do that. Or what do we learn with a regular diode in our meter? Can we identify which is the cathode, which is the anode by doing the diode test? It's still a diode, so the test still works the same way. Works all the same. We test them the same way. Now, with our meter, when we test them, our meter's not going to supply enough current to turn on or to light up the LED. But that's okay. We don't sweat that. You should have at least 3 LEDs in there. It should be a yellow or an orange one, a red one, and a green one. They're basically all about the same. They're just different colors. So test those with your meter and see if it lines up with the long lead and the short lead, if they turn out about the same. And you should see what kind of resistances that you see, or the same kind of resistances you saw before as you test those different LEDs. And then we're going to convert that little power supply we just did into an LED tester and see if they actually light up. Okay, so go ahead and get your meter, test the LEDs, and let's see if it works. Okay, we ready to move forward again? Let's do something else. Here we go. Let's talk transistors now. We played diodes, things go in one direction only through diodes. What about a transistor? Transistor, generally they're broadly rounded. There are 2 types that we talk about, PNP and NPN. You remember that PN junction that we showed, the little block diagram of a diode that had P material on one side, N material on the other? When we do a transistor, we just basically do the same kind of thing. We have P material on one side, a semiconductor piece in the middle, and N material on the other side. So hence the name NPN, PNP. The way you can tell by the schematic symbol is which way the little arrow points. Notice the little arrow here on the emitter. Current will always flow into the arrow, so current would flow this way and up to the collector. For this one, current would come from the collector and flow down, going the opposite direction. So that little arrow point lets you know which way the current is going to flow. And sometimes you use one in an application, sometimes you'll use another. And there's all kinds of ramifications on how you can hook these things up. Okay, a transistor has 3 poles or 3 connections called the collector, the base, and the emitter. Current always flows between the collector and the emitter, one way or the other. It may go up and down, from emitter to collector, or the other way around. But the base is the gate that controls it. The base voltage controls how much is going to flow through that particular junction. So that's how we can take a small signal and amplify it. We put the small signal's value into the base of the transistor, and we read the value coming off either the collector or the emitter of the transistor, and that will be much greater than the input was. So use that small signal to control the transistor to give us a much greater output for amplification. Okay, types of it, germanium and silicon. You don't see many germanium transistors anymore. That's pretty much old technology. Everything's pretty much silicon now. Silicon's much less sensitive to static and will handle a lot more current than germanium ever would. Collector, emitter, and base, which we talked about already. If we equated that to a vacuum tube, in a vacuum tube you have a plate, a cathode, and a grid, and the grid controls the flow between the cathode and the plate. Here, the base controls the flow between the emitter and the collector. Losing my voice, sorry. Okay, so how does this thing work? This is just a basic little 1 transistor amplifier. We have a small signal coming in on the input. Notice the capacitor on the input. There's a reason for that capacitor. If that capacitor were not there and the input had a DC component to it, had some level of DC on it, then that would change the bias voltage or the voltage on the base of the transistor and totally change its amplification factor. So we put the capacitor there, that lets the alternating current signal go through, blocks the DC. And then the R1 resistor there helps to establish the voltage for the base. So we have that signal, a little small signal hitting the base. And current is flowing against the arrow point from ground up through there. Notice the load resistor at the top. That load resistor is much like we use with the LED. That load resistor keeps too much current from flowing through the transistor. Plus, it's also then the transistor acts kind of like a Zener diode in that it varies its resistance as the signal coming in varies. So as a lot of signal comes in, it makes this a lot more current flow, and we get a big signal coming out. Notice the signal is inverted. On the left, when the signal goes up, when it comes out, it goes down. I mean, they're out of phase. You're doing good. I'm sorry. Okay. Just your basic transistor amplifier. Now notice the C2 on the end, the output transistor, same thing. That keeps the DC component that's running between the transistor and the power supply, keeps that out of the gaining the next stage. So we could actually cascade, as we call it, several of these together to keep building the signal and building the signal and building the signal and get it bigger and bigger. Now, this is just for illustration purposes. This is not a real circuit, if you please. Good. Yeah, it's pretty basic, pretty elementary. Normally, one of the key things we have to deal with is called base bias, the amount of voltage when nothing's happening that we apply on the base of the transistor. And normally you'd see a resistor coming off up here and down, and another one down to here, and would set the base bias value to some fixed value. And by adjusting that, we can also adjust the gain of the transistor to a large degree. But that's the basic idea behind a transistor. Each component does have a reason that it's there. Any questions about that? Does it kind of make sense? Hopefully. Sort of. Okay. Put it into a little bit more practical situation. A little one transistor amplifier putting a signal into some headphones. We might have an input from this might be our crystal radio, which is a very low level signal coming into that thing. Notice they have the input capacitor on the input side, takes care of any DC that might come in. What do you think might be the reason for this little 500 picofarad small value capacitor on the base, on the input there? What's its function in life? Noise filtering, precisely, primarily for RF. If there's a lot of RF in the circuit, and radios are all about RF, let's face it, that little capacitor would drain off any RF and take it to ground and get it out of the way, leaving us a clean audio signal to go through. Notice in this one, though, we do have a 2.2 meg bias resistor there on the base of the transistor that provides at least a measure of bias voltage, a stable bias voltage. Still got the 3.3K resistor up off the collector, which is acting as the balancing agent. There you got the transistor and then the resistor. And essentially, if you looked at that voltage that's in between right there where my thumbs are, that voltage is essentially doing this, going up and down in sync with the input signal. Okay? So we come out of the collector in this case, go through another 0.22 microfarad capacitor, which keeps the DC current from the battery from going through the headset. And we have a little bit of amplification. We hear it better in our headset. In this particular case, they're just using a 9-volt battery to explain it. Notice the little comment over there on the right. Build this amplifier on a 1-inch square piece of printed circuit board. Could you do that? Wouldn't, yeah, a 1-inch square, that's, a very small little piece of circuit board. One of the things we do if we ever get to do our soldering class, so we'll try to bring in some things called perf boards. They're perforated boards, phenolic boards, with little holes drilled all in it about every 1/10 of an inch, and a small little piece of metal that's attached as a solder pad, and you would solder things to that little perf board to make a circuit out of it, make it nice and compact. So that's what they're talking about. You're taking a 1-inch piece of perf board, that little special board, putting the components in there, soldering them down. You could actually do that and make a little amplifier like this, and it would work. Not totally efficient, it's not the best design in the world, to say the least, but it would work. And then notice some of the transistor things that's at the bottom. It's just FYI and gee whiz. The 2N2222A, which you have one in your package, by the way, is a very, very common transistor. All those B number transistors, the BCY and let's see if there's any others. That's the only one. Any of the BC types generally are British numbering transistors when you see those things. Most US transistors are numbered with a 2N something or another. The MPS oftentimes will be a different type of transistor. We'll talk about that in just a second. Whoever did this, or saying you can use any of these transistors that work for this particular circuit. It's not real critical which one you use. Okay, a variation of that one was called a junction transistor. We also have a field effect transistor, which more resembles a tube circuit much more so than the other one does. It has a very, very high input impedance on the gate circuit. This uses, you notice, gate, drain, and source instead of base, collector, and emitter, but it does the same thing. The biggest difference, though, is the gate impedance is very, very high. The base impedance on a regular transistor is quite low, which means that if you hook that transistor with a collector base emitter to a circuit that's very sensitive to any load on it, it'll load it down. Where this one has a very high input impedance, a very high resistance, it won't load the output of another circuit quite so much. FETs are often used in test instruments for that very reason. It gives you a higher input impedance to make it work. But other than that, as I said, it works pretty much the same way. The difference between the N channel and the P channel, as they're called here, is which way the gate arrow is pointing. And you do have, by the way, you do have an FET in your package there. It's called an MPF 102, I believe it is, which is a field effect transistor. Field effect amplifier works just like the other amplifier did before, just using the MPF 102 FET instead. If the little capacitor on the input keeps the DC from coming through. R3 gives you a little bit of base bias, steady voltage on the gate. In this case, we put a resistor both the top and the bottom to limit the current through that FET and take the output off the drain. Goes through a small capacitor, keeps the DC out of the next circuit and up the chain. But it works basically the same way. Okay, how do we test transistors? Very carefully, right? A lot of the multimeters have little transistor testers built in. You can use those if you want. I don't generally. I tend to be minimalist, and I just test it myself. So if you look at the transistors, and you may need, you should have 4 of them. These little tiny things look like that. You should have 4 of them. You should have a 2N2222A. You should have a 2N3904 and a 2N3906. And an MPF 102. And again, like I say, you may need a magnifying glass to see that.
All you need is 3 different colors, 4 different colors of nail polish.
4 different colors of nail polish. I didn't thought about that, but it works for me. On the handout that you have that looks like this, it will help you identify what the leads are on those 4 transistors. We're going to test them using the multimeter. So in order to know which is the base, the collector, and the emitter, you can look at the picture like that. On this one, the 2N2222 shows a picture of it with the flat facing you. In that case, they label the legs of the transistor 1, 2, and 3. 1 is the emitter, 2 is the base, 3 is the collector. So how are we going to test this thing when we get ready to test it? Wrong direction, sorry. Back to there. Okay, so when we get ready to test this thing, there's several different directions we're going to test. We're going to take our meter and test forward and backwards. That means we'll put the leads positive to one of the leads, negative to the other, and then reverse them the other way. So we'll check the voltage, the resistance between base and emitter, between base and collector, and then we'll check between collector and emitter. Idea here being that we go from collector to emitter. If we get zero resistance, that means it's shorted out. It's no good. When we go from base to collector, base to emitter, we should get a small reading, kind of like a diode, letting you know that it's okay. So we're going to test those. Now, 3 of those you can test. The 2N3904, 2N3906, and the 2N2222 are all PNP or NPN standard transistors. That'll work. When you get to the FET, though, the FET is a problem. It doesn't work that way. Don't test it like that with the meter, other than to test it to see if it's shorted or not. So how are we going to test the FET? Anybody? We're going to cheat. We're going to cheat. I have here at my disposal okay, we got 2 of these little solid state testers. Notice there's 3 leads on each one. You can hook the leads on the transistor in any order, it doesn't care. Press the start button, it'll tell you what it is, which one is the base, which one's the collector, which one's the emitter, and if it's good or not. It also works on the FET. So I've got these here, you can play with them, play with it when you get ready. Tim, pass that across, would you? I would throw it, but knowing I'm not good at throwing things, I'm not going to do that. The idea behind that, let's keep it rolling just a little bit. It's 10 after 11 already. As they say, time flies, doesn't it? Well, the frogs say time is fun when you're having flies. Okay, so we tested some of those things, played around. Now let's change horses, absolutely, totally, start over, okay? Opto-isolators. We want to talk about integrated circuits a little bit. The reason for choosing this as opposed to some other integrated circuit is this is fairly similar, when you look at the schematic of it, fairly similar to individual transistors. Whereas if we looked at an AND gate or an OR gate or an amplifier, a 741 op amp or something like that, the internal schematic would be very complex. So this gives us kind of an intro to integrated circuits, but still keeps us on a familiar playing field. So that's kind of why we chose this. This particular one is an LT827, LTV827. It's an 8-pin DIP. What does DIP stands for in this case? DIP, dual inline package, which means there's 2 rows of pins. If you look at that, that's that little tiny square thing that you have in your package. Looks like that, if you can see it from where you are, a tiny little thing. Go ahead and find that. Okay? There's a tidbit that I have to tell you about. Okay, first of all, that little tiny thing. It has legs on it. On the top it says LTV 827, right on top of it. Okay, got it? Okay, two things I want to tell you about that. Listen up just a second, gang. This is important. Yo-ho. Everybody listen up. This is important. You got to know this. Number 1, to identify pin number 1. We got 8 pins here, and they're all critical. You got to know which is which. Pin number 1, you notice there's a little dot there. That's over pin number 1. Okay, so they're numbered starting with that on that side, 1, 2, 3, 4, and go to the other side, 5, 6, 7, 8, going back up. So 1 and 8 are opposite of each other. I believe in your package there also may be a pin-out diagram of it.
What's the little 4-pin dip that most people don't have?
Pardon?
What's the 4-pin dual inline package?
I do have a 4-pin one. I bought some because I couldn't find any of these. Oh, you got the one with the 4-pin in it?
Yeah.
Okay, sorry. Okay, what? We're not doing sound today. Okay, all right, so that's the first thing. Second thing is, when you get ready to plug this into the breadboard, the pins may not line up. You put it in there, they're outside. I mean, it's like it's too wide. Okay, now watch carefully, because this is really important. The pins on that chip are kind of pointed out like this. That's how they come from the factory. They need to be bent in where they're straight like that. So how do you do that? You take the little chip and you lay it on a flat surface like the table, and you just rotate it just a little bit just to bend those pins in all four at one time. Turn it over, bend the other 4 pins in. So when you look at it then, instead of the pins looking like that, they'll look like this. Okay, so you want to bend the pins in just a little bit by rocking it on the table, and then it'll plug right into your breadboard. Some of them may already be bent because they've been used before, but some may not be.
It bridges the gap.
I like to put it across the gap in the middle of the board. Okay, pay attention. Pay attention to where pin 1 is. Just never lose track of where pin 1 is. Okay, now what does an optocoupler do? Let's talk about this real quick. Okay, ready? Not quite ready. Okay, let's look at this crazy optocoupler and talk about what does it do. Instead of having a base voltage applied to it, but to act as a switch to turn it on, turn it off, we use a light beam instead. Okay, so we have a little transistor. Notice you have a transistor inside there, but there's no base connection. The base connection is actually a little photosensor. You shine a light into that, it turns on. You turn the light off, it turns off. Cool. Where do we get the light to do that? Guess what this guy is? It's actually an LED. It'd been better if they'd put 2 little arrow points on there, but they didn't. They don't generally do that. So the idea is when I put a negative here and a positive there, turn this diode on, it emits a light to this guy, which turns it on, and then this acts like a short circuit between pins 5 and 6 up there. That makes sense? So what are we doing with this thing? Well, we're going to play with it just a little bit. This gives us the opportunity to play with an LED and a transistor and an IC all at the same time. So that's the idea behind using this particular thing. Okay, so what are we going to do with it? Back up just a second. Why would we need to do this? Why would we need to use an LED to turn on a switch? Well, yeah, but generally it's used for isolation. Where you have something going on this side of the circuit, you don't want any interaction with the other side of the circuit. You don't want an electrical connection between the two. So we can use this to turn one circuit to turn another circuit on, but have no electrical connection between the two. To isolate the two. Could be high voltage, it could be any number of reasons we want to do that. So this way, all we have between the 2 circuits is a light beam, which doesn't conduct electricity. So it gives us, that's why it's called an opto-isolator or an optocoupler. It can be called either one. Okay, so we're going to build up one of these things and see if we can actually make it work. So we're going to need the breadboard. You need the IC that we talked about. You need to be able to plug it onto the board. So if you need to bend the pins in just slightly so it'll plug in, you can. Now, those pins are pretty flexible. They can be bent and moved back and forth quite a few times, but they will eventually break off. So be careful. We're going to use pins 1 and 2 and pins 7, 8, so we're only going to use half of it. And you have the instructions in one of your handouts. If I can figure out which one it is. Okay, look, it's called optocoupler demonstration. Looks like this. This gives you the step-by-step instructions on what to hook up to where and to test it. We're using a switch on this one so we can switch it on and off just to make sure that we can see it actually works like we want it to. Okay? Okay, we're in construction mode. Go for it. We're going to use we're not going to use our power supply on this one. We're going to use the battery box. The reason for that is this is a 5-volt device. Using the battery box with 3 cells gives us about 4.5 volts, which is adequate.
Okay.
And it keeps it safe. So you have the battery box, 3 dry cell batteries to put in it. Okay, gang, let's see. We got one more little something we need to do here. Can we make the LED flash? Phase 2 here. Okay. That just says what we're going to do, what we did. Now modify it to flash, and that's that other circuit that you see on that same handout, a little further down the page. And you're going to modify it, so we'll do that. It's where you use the 5.6K and the 100 microfarad capacitor, which gives you a time constant, which determines the blink rate of the LED. So we're going to basically just modify it, and you should be able to get a blink. You don't need to leave the switch in unless you just want to. You can just put a jumper in place of the switch. And small modification to it, but it should make it blink.
The way you put it together.
Oh, no, I didn't notice that.
And we, instead of looking at parts with these kind of odd, non-intuitive connections, we just went by the numbers.
Okay.
Just what's this pin, what's this pin, what's this pin? Not worry about all this complexity, because you start trying to figure out all the wiring. This is fairly simple. You get a big circuit, you're lost,
Yeah, I bet.
just lost.
I
It works.
I can't read all this yet anyway.
Well,
Learn.
I labeled a little bit.
Yeah, I appreciate that.
His, yeah, like these are, I'm trying to use the same symbols.
Yeah.
So the squiggly line indicates a lot of wire. It's like,
That's why
we
they
got a
do it.
lot. It's like if you ever open up your toaster and you see
Oh, yeah.
the wire in there and they wrap more wire, okay, here we are wrapping more wire. So is that really a resistor? Well, it's more resistor. Close enough. Next symbol. Next symbol. You heard about the capacitor, right?
No.
Well, low-value capacitors are usually shown like this. If they're used in RF, they're just
Oh,
like
the
that.
can, the can.
No, just if they're like last time,
Yeah.
101. We had a really small value capacitor. It's in picofarads, 10 to the minus 12. I mean, really tiny. Okay? They just show it like this. If it's a higher value, like 1 microfarad, let's say, they'll show you a plus.
Oh, okay.
And it might be electrolytic, but it does have some polarity to the construction of what's inside here. This one usually has air or mica. This will have paper or oil or something in there.
Wow.
Then there's the one that is like this. And that goes back from like the 1920s and 30s when a capacitor, 100 microfarads would be this big.
Hand me the can.
Yeah, it was a
Curved.
can. It really was a can. They used
Yeah,
cans.
no, I remember
Because they
seeing
weren't
it.
going to make something new.
No.
Use what they had. So they used a can. And they crammed it in. If there was extra space, they poured in tar. Tar.
Okay.
Asphalt. And it was black.
PCB, we call
Well, it had it in it.
Yeah.
They didn't know what a PCB was.
it, back in the day, they
Yeah,
did
it just smelled good. And they stopped there. Notice the color. That's not tar. It's black.
You talking about the bottom of the can?
Yeah.
Okay.
See, it's black.
Yeah.
It could be any color it wants to be.
Yeah.
It's a synthetic plastic.
Did they make it black because?
It always was black, because it used to be tar in the 20s and 30s.
They just make it black.
So, I mean, it ain't broke, don't fix it.
Yeah, oh, yeah.
It worked for so long, and nobody knows.
Tar was cheap and it
It
was
was there.
non-conductive and it,
Yeah,
okay, and it held, it melted and then.
you could melt it, and it was
Cools down and it's a solid.
pretty much, unless it overheats. And then the guts flow out on your circuit, and that's exactly what would happen.
You're a really good teacher.
So that's why the color is that. Fortunately, they haven't changed the color, right?
I haven't done mine yet.
Look
It's
at
blinking,
that.
look at her go.
No, that's his.
Oh, that's his.
What is that?
You give her crumbs.
Welcome to
Sparkles?
Reading Schematics
Find
101.
them on the floor.
Oh, yeah. They must have had a birthday party in here or something.
Happy birthday, Ron. Okay, and this is the
That's the
idea
ground.
of a ground, like layers of earth. Very technical,
Must have done something
but it's sort of intuitive.
I bought a little book on what all these symbols
But-
are, but I haven't read it
Yeah,
yet.
but actually, this is called a circuit ground. If you were building something, say like what we may do at New Hope,
Oh, yeah.
Here, he wants to
there's
show you.
not only a circuit ground, there would be,
Again?
That's where he was going.
Chassis ground.
yeah, there'd be an earth ground.
No, the other one's the earth ground. This is chassis ground.
Oh, that's chassis?
Chassis ground is the three fingers
Oh,
diagonally.
okay.
The
So this
earth-
is chassis, and
That's,
this is,
that's earth ground or negative, yeah.
so but you'll never see this. You'll never see this on typical circuits,
Not on new
and
ones.
hobby circuits and stuff like that.
And you often won't
And
see it
even
on new stuff.
even HP doesn't use this as earth ground. They use this as circuit ground. Until they get to the really high impedance test equipment, then the really senior engineers come in and they straighten it out. So you look at its schematic for one device, you look at its schematic for another device, you go, wait a minute, what's going on here? Well, it's the level of expertise required. And a simple device, nobody cares. So in most equipment, they won't even show you the earth ground. But if it's like an electrical tester, say like a medical tester, I have a medical tester for,
This was not yours?
you can plug a device in, say like my coffee pot. Plug in my coffee pot, and it'll tell me what the leakage is from each wire to earth,
Yeah.
or between each conductor. And it has set in there, preset, the UL limits, safety limits. And if it's good, you get a green light. If it's bad,
Let me show you.
you get a yellow or a red light. It usually has a meter, so you get the actual number and you write that down on your test sheet.
Linking and linking, here
So if you're gonna certify it that it's safe for hospital use, like a patient, right? And they plug a heart monitor in, you wanna make sure there's no leakage, right?
Right.
So there's paperwork.
Because this will make a
There,
difference in how you.
they pay close attention to this.
So,
These are extremely different, and they're not connected. So they'll be isolated by maybe 1 billion
This one
ohms
came
or
out
10 billion ohms. A lot of, well, it doesn't take much to, defibrillate or fibrillate a heart.
Yeah, there's a defibrillator out there. Should we give it a shot? See if it leaks.
If your heart's in trouble, it doesn't take much.
No.
If your heart's good, it takes a few micrograms.
I,
Yeah.
So this is the photo transistor, and frequently what they'll put is,
okay, here's
to let you know what's driving the base, they'll put a lambda, which is the Latin symbol for L, which is
we
wavelength.
normally put pin 1 in the
What
upper
is
right,
driving
upper left
it? Is
hand.
something actually,
Just like.
Photons.
is
I'm gonna start with the LED.
Instead of the
because that's
lead
first thing.
picking
In case anybody wants to know, it will work.
pick up the light?
photons are coming in.
The blink. Oh, you got yours blinking already. All right, you did good. Okay, gang, let me go ahead and get your attention here for a second. I know some people are going to need to go, and it is after 12. Technically, we got a little more time in the room, so we're okay with that. Let me talk through the last section, and if you want to stay and play with this, we've got time. You can still do that, okay? But let me just talk us through this last section, and we'll go from there. I think it was Jerry was saying, playing, and Larry were playing with the blinking one. You know, if you put a second capacitor on there, give it more capacitance, it slows the blink rate down. And you can calculate that. Remember, there was an RC time constant. You do capacitance times resistance, gives you the time in seconds for the charge-discharge cycle. So you can actually calculate that. So if we use a bigger resistor, more capacitance, it slows it down. And the converse, of course, would be true. Smaller would make it go faster. Okay, so like I said, you can play with this, continue to play with that if you want to. We want to talk through this little transistor amplifier here. We could build that, but I think we'll omit doing that one today and just talk it through. Every component, of course, has a function or a reason for being. So, what's cool, lady? You got it blinking. All right. That is literally one of those cases where the light turned on. Nothing wrong with that. Okay, talking this little guy through real quick. Then you can go back and play with that some more if you want to. An electric microphone element is a capacitive type microphone element, but it requires power for it to work. Flea power, it doesn't take much power, but it has to have some kind of power. So to provide this microphone with power, we have that big old resistor at the top coming off our 9-volt supply, hooked onto here, and then the back side of the mic is hooked to ground. So there's a small amount of power applied to the microphone there. That gives it the power it needs. Usually I have a 10K resistor there. Usually that's more like a meg or two, very high resistance. Doesn't need much power, it just needs the voltage. Then we have a capacitor. Remember what the capacitor is for in a case like this on the input? It's going to keep this DC from going through, but it's going to allow the signal from the microphone to go through. Goes through there. Then our transistor set up there, we have our main dropping resistor up at the top with the power coming down, and I guess I really should face the camera the other way. I can do that now. So the resistor at the top is a dropping resistor to limit the current through the transistor, plus it also helps the balancing act as the transistor conducts more and conducts less, and this signal level here goes up and down in conjunction with what the mic is doing. Okay, and then also we have a bias resistor here, 100K ohm resistor, puts about a bias voltage on the transistor. If we wanted to make it more stable, we would put an additional resistor from there to ground and fix that voltage where that voltage can't vary. Okay, so as we're going along, the signal's coming into the transistor, making it conduct more and less. As it conducts more and less, that's reflected coming out here. This signal will be greater here than the signal coming in, that's why it amplifies. Now again, a capacitor there keeps the DC voltage from going through our speaker. But the speaker will take the AC currents, the sound value will still go through the speaker. So we speak into the microphone, and the microphone generates a very tiny little signal, gets amplified by the transistor, does invert it. So when a pitch goes high, it goes a low coming out and comes out the speaker. Now, in a case like this, you're not going to get a whole lot of amplification out of one transistor and a little dinky speaker like that. And plus, the speaker is critical. If you use an 8 ohm speaker, which is most of the standard little speakers you use, it's going to work a little bit, but not very well. You really need a 32 ohm or greater speaker, a higher resistance speaker. But since I don't have that, I only have an 8 ohm speaker. How can I work around that? How? Close. How about a transformer? If I use an audio transformer, what's a transformer? A little iron core with windings or wire on either side of it, right? Okay. So I use an audio transformer, which by definition, and by the fact that that's the way they're made, usually they're about 2,000 ohms on the input side. So it's a fairly high resistance, which would work real good in this circuit. And the output side is a much smaller winding with 8 ohms output. So 8 ohms into 8 ohms is a perfect match. The transformer also gives me a little bit of gain there as well, And so that works like a champ. So I can put a little audio transformer and make it work even better. And that's kind of it in a nutshell. Any thoughts about that? I mean, it's not that difficult, really. Okay, if we built it up, that's all the stuff we'd go through building it up. Back up one, went too far. Talked about diodes, Zener diodes, various other. There's a lot of other types of diodes we did not talk about, like SCRs and triacs and all kinds of other variations, but we talked about the main ones. Power supplies, doing a full wave versus a half wave power supply, filtering and so forth. Talked about transistors and playing around with those a little bit. And then the optocoupler, which let us play with the transistor and a diode all in one nice little integrated housing. What comes up next? Good question. If we do the digital principles class, the digital principle is even more hands-on than this one is. Again, we're using integrated circuits for that. We'll put them in the breadboard and set them up to do AND gates and OR gates and all that kind of stuff and show how we make decisions with digital logic. How do you count to big numbers just using ones and zeros? All those crazy things that we do. And we actually breadboard some of those things up and actually see how that works and see it happen. And so there's a lot of hands-on in the digital class. It's a good class, but you've got to work on it. We do also do a little regulated power supply to provide power for the things we're working on. Use a 5-volt regulator IC to give us a regulated 5 volts so the power is stable for the integrated circuits that we're working with. Logic tables, which are a little way of charting the thing out so you can see what a particular integrated circuit is going to do. And then what do they do? What happens? And of course, hopefully we're going to have a building class one of these days, maybe a soldering class first, and then a project class maybe sometime after that. So the alternate to the digital principles is a vacuum tube class. And we said earlier, but who uses vacuum tubes today? Well, not a lot. There's still some vacuum tube equipment out there. A lot of us keep that vacuum tube equipment because if we do get that big magnetic pulse, we'll still have radios that work with the vacuum tubes. Plus, a lot of our amplifiers are still vacuum tubes, so it's not a lost cause. But anyway, in the vacuum tube class, we talk about the construction of a tube, how they work. I have a real neat little video that some guy did that I think is fabulous. It walks us through a 5-tube AM receiver. And the good part about that is it shows us how a receiver works. All receivers are going to work pretty much that same way, whether it's vacuum tube or ICs or using a crystal oscillator frequency control somehow. It still works about the same way. Mixing, heterodyning as we call it, filtering things out, using automatic gain control. Those things haven't really changed much in all the years. And we talk about modulation types and some of those things as well in the vacuum tube class. Plus, I bring in a couple of vacuum tube testers and some tubes, and you actually can test some of those things. We bring in a couple of vacuum tube operated machines like a vacuum tube voltmeter. Works much like these meters we have here, except it's analog and with a needle. But it's vacuum tube, which means you got to plug it in, let it heat up for 10 minutes before you can use it, at least, for it to stabilize. And then it's analog. So if you're going to measure voltage, you got to be sure you got the positive on the positive voltage, and the negative. Otherwise, the needle will slam backwards, and you can bend the needle literally if it's too bad. So there's a lot of little stuff you got to watch out for. Also, with those analog meters, when you measure resistance, there's a zeroing resistance and an ohms adjustment you have to do. You zero the meter first, you short the leads together, and then you set that point, the 0 ohms point over here. I mean, it's a little more difficult to use than the stuff we're doing here with the digital world. But anyway, it gets interesting. It's an interesting class. We can do that if you want. I don't care. It doesn't bother me. If we don't do it, that's fine too. But you tell, what do you think? Would you rather do the digital or the vacuum tubes? What do you think? Both. I love your attitude, because that was the answer I was hoping somebody would say. I'd love to do both. What do we want to do next then? Let's put it that way. We'll do the digital next. Okay, we'll work. Jerry and I will work on that, and we'll try to figure out a good date, and maybe get it where it's not in conjunction with a holiday weekend as well. But we'll do the digital one. And as I said, there's a lot of hands-on with that one, with doing what we're doing here with the breadboards and the ICs and all that sort of thing. And that's kind of it in a nutshell. Any thoughts or questions?